So I want to talk more on this displacement scale. And now that we have got a normalization constant, we can also see what the wave function actually looks like. Okay, so here this graph is showing you what psi looks like in the red and what psi squared looks like in the blue. They both look very similar. They have the function of a Gaussian distribution because that's that e to the negative y squared divided by 2 term. That's what that's giving us. All right. And also, if you notice, when this displacement scale is unitless, so when it's set up as x divided by alpha, we get these really easy whole number integers we can see on the scale, like 2, 4, etc. Okay. And also, I'll just remind you, right, this model describes particles on a spring oscillating back and forth. And you can see from psi squared, what we get, the most likely place to find the particle, is somewhere in the middle. And as this displaces, as it stretches out, we find less and less probability of finding it there. So now what happens, so this is for the case of nu equals 0, which we're going to call the ground state. So now this is the case for nu equals 1. And so you can see psi is in blue and psi squared is in red. And you can see they both predict the same thing, all right? So very similar to the particle in a box model, we're now getting these integer waves, all right? And then now what you can also see is we have a node in the middle, okay? And so now if you look over to my Mathematica file here, let me go to this one here. I've got them labeled, all right? And so these are actual calculations. This is a pretty fun, cool little figure I made. So you can see here is that nu equals 0, that ground state, where the particle is predicted to be kind of right in the middle. And notice what happens as I go up to nu equals 1, I predict a node in the middle, and the probability distributions are moving out towards what I'm going to call the turning points. So the turning points are as it stretches out and then recoils, right? And stretches out and recoils. And you notice as we keep going up and up and up, we get smaller probability of finding the particle in the middle. So I know it's kind of hard to see, but these, for nu is 4, right? These 1, 2, 3 peaks in the middle, those are lower probability than the peaks on the outside, all right? Which is pretty cool. And so I want to talk a little bit more about this displacement scale and this whole notion of m, all right? Because what you might be thinking right now, I've been drawing these two masses on a spring, M1 and M2. So what does that mean for M right there? Okay. Well, recall, we have to use the reduced mass when we have a two-body problem like this. So this M we're talking about here is the reduced mass of our two masses, all right? And so I'll remind you, reduced mass gets the Greek letter mu, and that goes as M1 times M2 over M1 plus M2. And of course, if M1 equals M2, then my reduced mass just becomes the mass, right? It becomes the same parameter, okay? Or excuse me, let's work that out. So if M1 equals M2, we'll just now say it's M times M over M plus M, which is M squared over 2M, yes, which is 1/2 M, apologies. Yeah, so if M1 equals M2, then we know the mass is just 1/2 M, okay? And if we go through our dimensional analysis, all right, this M has to be in units of kilograms per single thing. So if we're talking about electrons, that's got to be a kilogram mass of one single electron. If we're talking about atoms, which we will very shortly, it's got to be the kilogram of one molecule. So we're not talking about kilogram per mole. We're talking about kilogram per one single thing. All right? So now, what if our two masses are very different? And I'm going to draw up a cool example. What if my mass 1 is, I'll say, mass of a proton, and what if my mass 2 is mass of an electron? Well, those two masses are very different. They're different by a factor of about 1,000. So mass of the proton is much, much greater than mass of an electron. And so what if I was describing this, right? I have this picture where I've got a proton and an electron, and perhaps the electron is oscillating back and forth with the proton, okay? Maybe as it's orbiting around our nucleus, right? We're going to start trying to build this physical picture. Well, what is the reduced mass of this pair? All right. Well, as it turns out, the mass of the electron times the mass of the proton divided by the mass of the electron plus the mass of the proton is basically just equal to the mass of the electron. That's right, okay? And the reason for that is because the mass of the electron plus the mass of the proton, right? The mass of the electron adds hardly anything to it. It barely changes the number, okay? And so because the mass of an electron plus the mass of a proton is basically just equal to the mass of the proton, then mass of the proton and mass of the proton cancel, and you just have an object that's only the mass of an electron. So what does that object look like? Well, it doesn't look like this picture that I drew with two masses on a spring. What it really looks like is some massive object that I'll call mass 1 that's fixed, okay? And now mass 2, in this case would be the mass of the electron, is now oscillating just against this fixed mass, okay? So in this example, right, of this like electron system, one electron system, let's say, it appears as our nucleus, or our proton, if you will, is stationary. It's stuck there in the middle while this electron is oscillating back and forth. So now as you look at this model, what I want you to imagine, nowhere in this picture is the proton, okay? Rather, if I go back now, and if we think about this picture right here, so here's my potential energy, okay? So my electron, what it's really doing is just oscillating back and forth between those two turning points. So, you know, here's my nucleus, some stationary object, right? And so now my electron just looks like it's oscillating back and forth right here, giving me my displacement scale. And also you can see based on the wave functions, it kind of makes sense that in the ground state, we predict it to be somewhere there in the middle, right? Oscillating somewhere in the middle of that displacement, okay? Which is pretty cool. And what I also want to say, what we can expand on this, we don't just have to use this model applied to protons and electrons. We could apply this model to actual molecules, all right? Which is pretty cool. So here, I kind of spoke out of order. So here, you know, I'm showing you the Mathematica file over here, but here's the results of it, of psi squared, right? And here is just psi, okay? And what's important to note, as nu gets bigger, we see more probability being pushed out to the turning points, okay? So more and more and more displacement as nu gets bigger. And what that means, that displacement, you know, we're talking about this displacement scale just now, right? So that depends on the oscillator strength, Kf, also depends on the mass, right? If we're talking about this electron-proton system, or maybe we're talking about hydrogen chloride, you know, a hydrogen and a chlorine vibrating back and forth, okay? And so what we expect, anytime we have two very different masses, one very light mass, one massive mass, this is what our picture looks like. And these types of physical systems that have this picture where one mass is much greater than the other, as it turns out, those types of systems follow this harmonic oscillator model beautifully. And the predictions we can make of these types of molecules is confirmed with spectroscopy with crazy precision and accuracy. It's awesome how well spectroscopy, or really I should say how well quantum mechanics predicts what we observe in spectroscopy. And I'm going to show you some examples of that soon.